4.7 Lesson 2, Graphs and Derivatives of Implicit Relations. Our objective for today is you'll be able to find derivatives of implicit relations by using implicit differentiation. So yesterday we learned about explicit relations. Explicit relations are those in which y is isolated. And we also learned about implicit relations. Implicit relations are those for which y is not isolated. In an explicit relation, you have y isolated and y is defined as a function of x. In an implicit relation, that is not done so. So you may be able to isolate y, maybe not. But in either case, you can use something called implicit differentiation to find dy dx for an implicit relation. And today we're going to take a look at two additional examples for finding derivatives of implicit relations by using implicit differentiation. Our first example is to find dy dx for the implicit relation e to the xy is equal to cosine of y. So we will follow these guidelines for implicit differentiation that we learned about yesterday. We will begin with step 1, differentiate both sides of the equation with respect to x. So we will write the derivative with respect to x of the left side of the equation equal to the derivative with respect to x of the right side of the equation. So when you look at the left side of the equation, you should see that we have a composition of functions. The outside function is the exponential function with base e, and the inside function is the product x times y. So you need to use the chain rule because you have a composition of two functions. So you take the derivative with respect to x of the outside function evaluated at the inside function, so that gives you e to the xy, and then you multiply by the derivative with respect to x of the inside function xy, which is a product. So to find this, in our next line we will have to use the product rule. But before we get to that, on the right side of the equation, you should also observe that we have a composition of two functions where the outside function is cosine and the inside function is y. And we make the assumption that y is some differentiable function of x, whether we know what that function is or not. We assume that y is some differentiable function of x. So we see cosine of y as a composition of two functions. So we will take the derivative with respect to x using the chain rule. So begin by taking the derivative of the outside function. The derivative of cosine is negative sine. Evaluate that at the inside function and multiply by the derivative with respect to x of the inside function y. So now for our next line, we will go ahead and find this derivative using the product rule. And one thing for you to understand is e to the xy is being multiplied by the derivative of the product xy. And the derivative of the product xy will have two terms. So make sure you distribute e to the xy to both terms from the derivative of x times y. So using the product rule, we find the derivative of the product x times y. So we have the derivative of the first function times the second plus the first function times the derivative of the second. And then on the right side of the equation, we have negative sine y times the derivative with respect to x of y. And here's what you need to understand. This is actually what we're looking for. The derivative of y with respect to x is dy dx. So in our next line, we do the following. We have e to the xy times the derivative with respect to x of x is 1. So that gives us 1 times y, or just y, plus x times Once again, this is what we're looking for. It is dy dx. And that's equal to negative sine y. And once again, this is what we're looking for. It is dy dx. So we have done step 1. We have differentiated both sides of the equation with respect to x. Now we go on to step 2. Collect all terms involving dy dx on the left side of the equation and move all other terms to the right side of the equation. And then after that, we go on to step 3, factor dy dx out of the left side of the equation, and finally solve for dy dx. In step 2, we'd like to move all terms that have dy dx to the left side of the equation. So this particular term has a factor of dy dx, and on the left side of the equation, remember what we said earlier. You have to distribute e to the xy to each of these two terms, and one of them will have a factor of dy dx. But we will begin by go ahead and distributing e to the xy to the two terms inside the brackets on the left side of the equation. So when you distribute e to the xy to the first term, you will have y times e to the xy. And when you distribute e to the xy to the second term, you will have x times e to the xy times dy dx. And on the right side of the equation, you have, of course, negative sine y dy dx. So to move all terms that have dy dx to the left side of the equation, I first identify the two terms that do have dy dx in them. Those are the two terms. So what I can do is I can add sine y dy dx to both sides of the equation, and I can subtract y times e to the xy from both sides of the equation. That would achieve my goal. So when I do that, I will have x e to the xy dy dx plus sine y dy dx, and that would be equal to negative y e to the xy. So I have achieved my goal of moving all terms that have dy dx to the left side of the equation. The third step is for me to factor out dy dx from the terms that have dy dx on the left side of the equation. So there are two terms with dy dx on the left side of the equation, and I will factor out dy dx from each term. So when I factor out dy dx from the first term, I'd be left with x times e to the xy, and then when I factor out dy dx from the second term, I'd be left with sine of y. So now we will go ahead and write that, and let's go ahead and make some space down here. So we will do step 3 down here, and I'll write that in green. So I will factor out dy dx. From the left side of the equation, and from the first term I'm left with x times e to the xy, and from the second term I'm left with sine y. And on the right side of the equation I have negative y times e to the xy. So now I'm ready to do my final step, which is, of course, to solve for dy dx. And that can be done by dividing both sides of the equation by the factor that is multiplying dy dx on the left side of the equation. So when I do that, I get my final answer, dy dx is equal to, when I divide the right side of the equation by the factor multiplying dy dx on the left side of the equation, this is what we will have. That is the final answer, and you can leave it like that, or you can express it in a different form if you prefer. An alternative form in which you can express this answer takes this observation. In the answer, you have in the numerator a factor of e to the xy, and in the denominator for the first term, you have a factor of e to the xy. The way we have the answer now is perfectly acceptable, but you can also write the answer in an alternative form that is equivalent, because you can replace e to the xy, if you prefer, with cosine of y, because in our original implicit relation, we know e to the xy is equal to cosine of y. So if you prefer, you can write the final answer as follows. You can write dy dx is equal to negative y. E to the xy can be replaced with cosine y over x times cosine y plus sine y. What you cannot do is, at this point in time, you cannot cancel these two factors of cosine y because of the plus sign that you have in the denominator. Alright, so now we look at our second example, and here's what we have. Find dy dx for the implicit relation given by sine squared x plus cosine squared y is equal to 1. So we will follow these 4 steps, and we begin with step 1, differentiate both sides of the equation with respect to x. So we write the derivative with respect to x of the left side of the equation is equal to the derivative with respect to x of the right side of the equation. And on the left side of the equation, you have 2 terms. So you're going to write the derivative with respect to x of sine squared x plus the derivative with respect to x of cosine squared y, and that's equal to the derivative with respect to x of 1. So this is really easy. The derivative of a constant is 0. And for this term here, you have to understand that sine squared x is a composition of 2 functions, where the outside function is the power function raising to the second power, and the inside function is sine. So you will be using the chain rule. And here, you have a composition of 3 functions. The outside function, like with sine squared x, is raising to the second power. The middle function is cosine, and the insidemost function is y, where y is assumed to be some differentiable function of x, whether we know it or not. So we're going to use the chain rule for both of these to find the derivative with respect to x. And of course, our goal is to solve for dy dx. So we will begin by finding the derivative with respect to x of sine squared x by using the chain rule. So we take the derivative of the outside function evaluated at the inside function and multiply by the derivative with respect to x of the inside function. And then we go to the derivative with respect to x of cosine squared of y. So we will have to use the chain rule. We begin by taking the derivative of the outside function evaluated at the inside function and multiply by the derivative with respect to x of the inside function, which is a composition of two functions, with cosine being the outside function and y being the inside function. And on the right side of the equation, the derivative with respect to x of 1 is 0. So now we will go ahead and find the derivative with respect to x of sine x, which is cosine x. So that gives us 2 sine x cosine x plus, I have now 2 times cosine y. We must find this derivative now, and we have to use the chain rule because we have a composition of two functions where the outside function is cosine and the inside function is y. So the derivative of the outside function is negative sine, and we evaluate that at the inside function of y, and then we multiply by the derivative with respect to x of the inside function y. And in the next line, we will go ahead and write that this right here is what we're looking for. The derivative of y with respect to x is dy dx, and that's what we're looking for. So we have 2 sine x times cosine x, and when you multiply all of the factors for the second term, there is a negative factor, so this will become minus 2, and I can either write cosine y first or sine y first, it doesn't matter. I think I will go ahead and write sine y first. So I will have sine y times cosine y. It just looks more consistent with what I did for the other term. But mathematically it doesn't matter. So now the other factor is what we're looking for. The derivative with respect to x of y is dy dx, and that is equal to 0. Now we're ready to move on to the second step. Collect all terms involving dy dx on the left side of the equation and move all other terms to the right side of the equation. There's only one term that has dy dx, and it's this one. You could leave it on the left side of the equation, or you could move it to the right side of the equation. It doesn't really matter. We don't actually need to do step 3 for this problem because there's only one term that has dy dx in our equation here. And then all we really need to do is just solve for dy dx, and that will give us our derivative of y with respect to x that we're looking for. So we can move this term to the right side of the equation by subtracting it from both sides of the equation, leaving us negative 2 sine y cosine y dy dx on the left side of the equation, and on the right side of the equation we will have minus 2 sine x cosine x. And then step 3 is to factor out dy dx from the terms that have dy dx, but again, since we only have one term with dy dx, we don't need to do step 3 for this problem. And step 4 is to solve for dy dx, and we can do that by dividing both sides of the equation by the factor multiplying dy dx. So that would give us dy dx isolated on the left side of the equation will be equal to negative 2 sine x cosine x divided by negative 2 sine y cosine y. And one thing that you can do is you can cancel the common factor of negative 2 to simplify, and that would make your final answer what you have now. You can't do much more than this because the arguments here are different, so you just have to leave it as you see it. That's your final answer. Today we looked at 2 additional examples for finding derivatives of implicit relations by using implicit differentiation.